Good morning, everyone.
Morning.
Good morning.
Is the Zoom link not on the class website, Adam? Oh, it's on Piazza. Every time I have to dig the first Piazza. Oh, you know what you can do? You can create a calendar. Put the Zoom link on your calendar. Make a recurring event. So every day when you need to go to class, you go to that day, you click on the Zoom link and it's there. Don't we have a class calendar? That's the only way I can find my Zoom links in my calendar. Otherwise, indeed, too much digging is involved. It's on the class calendar. Okay. Excellent. Organization is key. So it's on the class calendar, Adam, and you can create your own calendar entry. And yeah, after that, your life will be easier. No lab this week, that's correct.
Good morning.
Good morning, Nikki.
Can everybody see my screen?
Yes.
Can everybody see my video?
No. Oh, your video. Yes, we do.
Why are you lying? Don't lie.
Not mine. I thought you were asking if it was playing a video, and then I realized it's your live video of you on your white shirt. We can see you. Yes.
That's right. I have a white shirt. Okay. Are we ready?
Oh, prepare your ears, everyone. Go, Mickey.
Welcome, EECS 16A. Woo!
Take a deep breath. Enjoy the day. Today's my favorite lecture. You know why, Anna?
No.
Every lecture is my favorite lecture.
Oh.
It's just getting better. It's just getting better.
Okay.
It's good stuff. It's good stuff.
Mm-hmm.
All right, so we're not going to cover Gaussian elimination today. We already did that.
What happened? That was such a short favorite lecture, wasn't it? My favorite too. We learned so much. Well, we learned that we're not going to cover Gaussian elimination. Yeah. I guess he went to correct the slides. And
Wow.
oh, you're back.
Well, it was like a Houdini thing that I wanted to do on purpose. because yeah, because it's fun. Today's a holiday, at least for me or for some other people. And it's a wonderful holiday. It's the beginning of the year, of the Jewish year. And let me just set up my thing again because everything got removed while I disappeared for a second. So I apologize for that. And now I can see it all in a lovely way. And there you go. And you know, just hoping that it won't happen again. So first of all, everybody, Shana Tova, happy New Year to everyone. On the right-hand side is a 3D rendering of a pomegranate that was acquired using an MRI, which I think it's pretty amazing, right?
Pretty cool.
Yeah, I know.
We start the year with MRI images. Yes.
MR images.
MR images, sorry.
Yeah, you don't want to say MRI images. You know why? Because MRI means magnetic resonance imaging, and if you say magnetic, oh, I guess you could say that. Anyway, all right, let's move on. Again, don't forget we have a quest coming up. Okay, what is your quest? What is your favorite color? Okay, what is the capital city of Assyria? Okay, all of these are valid questions on the exam. All right, last time we talked about Gaussian elimination, and we also started talking about vectors. I kind of rushed pretty quickly through it, which is fine because, well, not fine, but again, I apologize for this. What happened was that because of the beginning of the class, the semester, and the fact that we started the last week, you know, the discussion, we're a little bit ahead of the lectures, and now that's been fixed by Labor Day. What we're going to do today, we have a pretty good set of things that we're going to cover. We're going to continue vectors, but combined with matrices, and we're going to talk about matrix multiplication, matrix vector multiplication, and then look at them as a way of representing linear set of equations. Okay, and there's a really interesting way of looking. So matrices are just numbers. We'll talk about that. But there's really different ways that you can look at those matrices. And they give you so many nice interpretation. So pretty nice. And then at the end, we're going to talk about
Oh dear. What happened?
Maybe it's another trick.
You know, we're neighbors. And he keeps saying, why don't you come to my house? Then we can lecture, you know, and from the same room. Imagine that. My internet's so much better, he says. Yep. Supposed to use MRI. Fine. He'll come back.
I think somebody wanted to, you know, give me a little bit of fun on the holiday, huh?
Yeah, maybe next time you come here to teach.
I don't think it's the internet or something. I think it's just something off with my, you know, we have a good friend called Anita Flynn. It's a really good friend, and she always says that the world is just a connection problem.
Cool.
So, which is true. All right.
Okay. Today.
Yeah. So we'll try to not have a connection problem here and see how it goes. You know, these are some of the things that, you know, you kind of dream about, that, yeah, they could happen, but like you hope that they don't. And when they come, it's like your heart starts racing. So yeah, it happens to faculty too. So my heart is kind of going at a high speed over here right now. Okay, let's talk about vectors. Can we see everything? Everything's okay? Yeah.
Maybe I should teach. I have the slides somewhere here. I'll download the slides. Mhm. No longer his favorite lecture. Let's see what's going on.
That is going to be interesting today. I know. I'm going to, instead of trying to use my iPad, I'm just going to use my, I'm going to try to use the just my computer. And so I won't be able to write so much today, but I think that would be a better way of actually delivering a lecture in a way that it's actually maybe delivered. We'll see. Again, apologize for this, but that's what the situation is right now. Okay. Okay. Great. Okay. All right, we went through that. Vectors. Okay, so vectors are effectively an array of numbers. I'll put the chat so I can see you kind of babbling. Oh, poor Mickey. All right, it's an array of numbers. It's just represent a number. It's just a list. And that list can present many things. For example, this particular vector over here can be just plotted as a vector that, you know, coordinate 3 and coordinate 2. So just a set of coordinates in dimension 2. What are matrices? Well, matrices are also a collection of numbers, but those numbers are just oriented in 2 dimensions. Okay. You've seen matrices before. It's not probably the first time you've seen it. We've seen it in a way that we just wrote this, but the way to write it is that we often will use capital X or some capital letters representing matrices, and then the elements of those matrices will have small letters, and then instead of having a single dimension, we say that X is in the real, so the real space, or in R, n by m. This is an n by m set of matrix. Can everybody see me? Is that okay? Yes, okay. All right, but if you actually think about it, those rows over here, those columns over here, each one can also represent a vector. Can also effectively be a vector. So we can basically take those vectors and stack them one next to each other. Okay, just stack those vectors one next to each other, and that would give us the same thing. So x1, 1, x2, 1, and so on and so forth can be called x1. And so, and then we'll put them next to each other, and then this also be a matrix. This is another way of viewing a matrices, which will be important in interpreting those linear equations. Okay. All right. So when matrices have the same size, they can be added element-wise. And now I will probably be writing things, and I'll try somehow to do that.
You want me to write?
Oh, you want to write on it? Yeah, go ahead,
Yeah.
Anna. Yeah. So what will be then, if I want to add x plus y, what will be the first element over here?
Let's see. Yeah, go ahead.
1, that's right.
Mhm. I have a, it doesn't let me annotate.
All right.
Okay, try.
You know, when it doesn't work, it just doesn't work. You know what I mean? All right. So the element here would be 1. If I add 1 minus 1, I'll get a 0. So there you go. Oh, magically, that appears. And so minus 2 plus 3 would be equal 1. 1 minus 1 will be equal 0. 1 minus 1 will be equal 0. And 3 minus 2 will be equal 1. And in this particular case, we ended up with an interesting matrix, which is also called a diagonal matrix, but it also has a different name. Anybody has an idea? Yes, somebody said, thanks, Anastasia. She said it was an identity matrix. That's right, that's a special matrix. And then scalar multiplication by all elements, if we take 2 times x, basically we'll be multiplying each one of those elements, and that will get 6 minus 2, and minus 4, as you have probably seen in the past. Okay, let's move on. Now, vector multiplication. Okay, so the thing is, with you want to multiply 2 vectors, you cannot just do like it has a size, like they have to fit with a certain dimension. And I had this math teacher, math faculty back when I took my undergrad, and he had this really, I mean, he was pretty big person. He was sweating a lot, and he go like, and he said it in Hebrew, but I'll try to translate that to English. In matrices multiplication, you go like this and like this. All right, like this and like this, or like this and like that. All right. So effectively, the width of the first matrix must match. The width of the first vector, which has to be either a row or column, but its width must match the length of the second. Okay, so these dimensions must match, and if they don't match, that's what you get. All right. If they don't match, it just doesn't work. It's beep, beep. It doesn't let you. For example, like when you want to annotate today, like it just doesn't let you. All right. Well, what can you do? Oh, I promised that I'm going to reduce the volume. Okay, I'm not going to do it again. All right. So from your point of view, okay, because now I'm looking at you, but from your point of view, if everybody raise their right hand like this. Straight. No, straight in front of you. Straight, not up. Yeah, straight. Like this and like that, right? Like this and like that. And you see that where your thumb is going to be multiplied where that thumb over here. And the where your index finger is going to be, that's going to be multiplying in the same coefficient as where the other index finger is going to be. Remember that. It's extremely, when I look at matrices, even today, I go like this and like that. That's why I remember that. Okay, so it's great. So let's say we have now 2 vectors in Rn. Okay, so they're n length vector, and we want to compute y transpose times x. Okay, well, y transpose is a 1 by n vector, and we're going to multiply it by n by 1. Do these match? Well, you go like this and like that, and yeah, it looks like the dimensions match. And what I'm going to do is I'm going to look first of all at my thumb, and I'm going to have y1, and y1 is going to multiply by the other thumb, and that is x1, and that will give me y1, x1. And again, I would have nicely annotated this for you if only the world will give me the opportunity. And then you add it to y2, and then your second finger. So second finger is on y2, it's multiplied by x2, and then it's added. And then all the way to yn multiplied by xn, so that's your tiny finger. And yn times xn. And so the number of elements must match. So if I have a 1 by m multiplied by 1 by n by 1, that would be not valid. Okay, so they do have to match. Okay, they do have to match. And so then you're going to get a full sum, which turns out to be a scalar that is 1 by 1. Okay, this operation, by the way, is also called an inner product or a dot product. And we'll talk about what it actually has a very strong meaning, very important meaning, but we're not going to talk about what that meaning is right now. Okay, so this is a row vector multiplied by a column vector. Okay, right, row vector, which is y transpose, multiplied by a column vector. Okay, so the question is now, what about this? What if I have a matrix? I have a matrix which is of dimension m by n, and I want to multiply it by a vector that is n by 1. Can I actually do that? Can I actually do that? Well, I mean, stare at this long enough and remember that A is a combination of column vector, but it's also a combination of row vectors, right? Like I can look at that matrix in different ways. And so I can do like this and like that, at least on the first row, right? I'm going to take the first row, at least that I could multiply, right? Because that would give me a valid result. Okay. So here's how a matrix vector multiplication works. Okay. Well, I have A times X. A has elements A11, A12, and all sorts of, all things like that. And what I'm going to do now is like this and like that. All right, this and like that. And I'm going to take A11 and multiply it by X1, and then add it to AY2 multiplied by X2, and so on and so forth. And I'm going to get this particular sum. Okay, this is the first row. Okay, like this from the top, like that. All right. Well, what I could do then is, well, I mean, I have another row. I love rows. Anybody like rowing? So let's just go row by row. All right. Before that, hold on. When I actually say A11, all that multiplied by this, I can actually say, oh, this is really this row vector multiplied by X. And let's just call it Y1 transpose. I mean, just to relate to what we did before. Okay. So now let's keep rowing. All right, now I can move to the second line, the second row, and I'm going to do like this and like that. And when I do like this and like that, I would get the sum of A21 times X1 plus A22 times X2, and all the way to A2n times Xn. How do you deal with matrix multiplication in more than 2 dimensions? Well, this is more than 2 dimensions. Hold on. This is, well, I mean, like there's many n's here. There's n by m. And then there's, there's more than, there's no 2 here. There's many dimensions. All right. So now we can just go row by row and compute all of these values till I get to the end. I'm going to do this and like that. And I'm going to get the coefficient A sub M1, X1, and so on and so forth. And you can see that the coefficients of A starts with, 1 by 2, 2 by 1, and all the way to M by 1. That's in the columns. And on the rows is, the second index is going to change. And here, X1 is throughout the entire way, and here X2, and so on and so forth. Now, what is this? This is, again, a collection of numbers. How many numbers? How many numbers do we have here? M. That's right. We have M numbers. And so the result of a multiplication between an M by N matrix and a N by 1 vector will be an M by 1 vector. So matrix vector multiplication will give us a vector. A scalar times a matrix doesn't give you a vector, it gives you a matrix. A matrix times vector gives you a vector. Very interesting. Okay, very interesting. So something pretty much happened to that vector X after being multiplied by this matrix, right? Like it's been transformed into something else. You took an N length vector, you multiply it, and it became an M length vector. Okay, we'll talk about that, meaning more about the class. Actually has a lot of stuff, okay, to do. Like, for example, I'm just going to throw a word here, projection. I just threw it, but just think about that. We'll talk about that more. So now we're getting to this question. Yeah, if you took one, Math 53, I mean, like, yeah, you should probably master this. By the way, there's probably 500 of you that have seen this material before, but there's also 500 who haven't. But here's the thing, we need to develop a language because we're going to talk throughout this class. I'm going to use all this in different applications. We're going to use this in circuits. We're going to use it in applications, so on and so forth. We need to develop a language. And so now we're building this jargon of, notation that will be able then to understand each other. And, there are actually different ways of writing the same thing in different disciplines. In chemistry, you would write vectors in a different way sometimes. They actually call them bra and kets, which is the weird thing because they just put them in a bracket. So one side is a bra, one side is a ket. A bra would be a row vector, a ket would be a column vector, and so on and so forth. So we need to develop this notation between us so we will be able to talk about it. Yeah, quantum mechanics, absolutely. It's all vectors, it's all linear algebra, folks. Good stuff, good stuff.
Best class ever.
Yeah. All right, so we want to multiply now an M by N matrix by an N by L matrix. Okay, we want to compute this. Can we? Can we do this? That's the question. Well, let's, from a vector point of view, remember that we said vector stuff? Let's see if things fit, right? So we're going to go like this, N, like this, N, yeah. So N, that works, it fits, okay? So those dimensions, this dimension fits. So perhaps at least I can multiply the first row with the first column. That's going to work, right? Okay. And we've seen that, I could probably multiply the second row with the first column and so on, but we can keep on going. So here's how we're going to do a matrix by matrix multiplication. We're going to start like this and all together like that. All right. And we're going to get the product, which is A11 times B11, A12 times B21, all the way to A1n times BN1. Okay, notice that the coefficient here is 1, 1, 1, 1, and then this one changes. It's the second index that changes. Here, the first index changes. Okay, and those will always match. Okay, now multiplying this will give us a scalar over here. There was a question if there was a difference, if the, if it's an N by M or N by N. Yeah, well, we'll talk about that in a second. Hold on, hold your, okay. So we multiplying this, we get a scalar. Now what we're gonna do? Well, I mean, I can either move down the rows or I can maybe move in the columns. Okay, so I'm gonna keep my hand here still, like this, still like that. You know, it doesn't move. Look. Well, a little bit. All right, but it's still okay. And then I'm gonna do like this and like that. But now I'm gonna move it, and I'm gonna move it by one column. Okay. And when I take this and multiply by that, the product will be, again, the same A11, A12, all the way to A1N, because I haven't changed those. So these will not change. The only thing that changes is now the indices of the B's. The B's is going to be B11, B21, sorry, B12, B22, all the way to BN2. Okay, so it's the second now. That index is being changed. Okay, the second. So along the rows, the second index are changing. And then I can do it again, like this and like that, which will give me, 3 points. And at the end, it's going to be like this and like that. And that's going to give me all the way to, you see, the first A doesn't have its indices change, but the B's will have their indices change all the way to L. Okay. And then, okay, am I done? Am I done? Am I done? No, I'm not done, because now I have another row to go. So I'm going to move to another row like this and like that, and like this and like that. And I would sweep this, that, this, that, this, that, this, that, and fill the second row of my result. And then I can also do just like the same thing all the way down, and kind of like a sewing machine, just like all the way down. So like this, like that, like this, like that, like this, like that, all the way till I fill the entire result. So a lot of multiplications here. Multiply and add, multiply and add, multiply and add, multiply and add. Look, these are all multiplies and adds, right? Multiplies and adds, multiplies and adds. You know that in assembly language, the language, the instructions that live on the computer, that the basic ones that the basic instructions that the computer will perform, there are a few of them, like additions, there's like multiplication, so on and so forth. But because the operation of multiply and add is so useful, people, when they design computers, they add an instruction specifically to do a multiply and add in a single computer cycle. You learn more of that about in CS61C. Okay. So yeah, I mean, this is such an important multiply and add type of operation. All right. So now that you know like this and like that, you can, if I give you two matrices and say, you know what, here is the multiplication between these two matrices. What is the result at location 2 by 2? Yeah, two matrices multiplied by each other are going to have, it's going to result in a matrix. What is this matrix size going to be? The matrix size is going to be an M by L. What is the value at element 2 by 2? Well, what you do is you go on the rows, you pick row 2, and you stick your hand there, and then you go like this, and you multiply it and add with the column, the second column in the other matrix. So you sweep, second, you multiply and add, and this would be the result. So now you know how to compute any element very easily and kind of jump around. Okay. So now hopefully practice this, this movement. I mean, just so your hand doesn't really get, too buffy. You could also try to do it the other hand, but like that doesn't matter how you do it. Just you can do all stuff like that. But here you really have to practice but be careful not to just beef up your right hand and not the left one too. Okay. So when I multiply two matrices, A times B, and if A is M by N and B is N by L, the second dimension here and the first dimension here must match. And the result is going to be whatever the first dimension of the first matrix is times the second dimension of the second matrix, okay? So n by n times n by L will give me an M by L matrix. All right? Perfect. Okay. Let's move on. So that's pretty exciting. Now we know how to multiply vectors. We know how to multiply matrices. We know how to multiply matrices and vectors. So let's do that then. Here's a case. Let's go back to vector-vector multiplication. Now, instead of having a row vector multiplied by a column vector, I'm taking a column vector and multiplying by a row vector. So x times y transpose. Is that valid?
Yes.
Yes, of course it is. You know why? Because you put your hand, you go like this, one, like that, one. Yeah, fits. Like this and like that, right? Like just one, but you know, one times it's like it fits, right? So that is pretty cool. And then you have to move to the second, and then you third, and so on and so forth. Basically, you start filling a matrix. So hold on. Before, when I had a column vector, a row vector multiplied by a column, I got a scalar. Now, when I do this, I get a matrix. What the heck? And that matrix is going to be size, in this particular case, n by n, because that was that size. If let's say y transpose was 1 by m, then I would have an n by m matrix. Okay. So here's the case when I have a row times a column, I get a scalar. A column times a row, I get a vector. This is called an inner product. So guess what this is called? Outer. That's right. And they do not commute. Basically, if I multiply one way or the other way, I mean, it's not the same. So it's not like scalars where a times b equals b times a. With matrices, it doesn't work. Sorry, with matrices doesn't work, but with vectors, it doesn't work either. Okay, so you have to realize this. Okay. So that is the situation. Yeah, so they don't commute. No commutative. Yeah, that's right. Vectors, you know, they're particular. You gotta watch out there. Ooh. Let's do an exercise. I'm excited. All right. You know why I'm excited? Okay, let's do this first one here. All right. Guess what? I prepared something for you. Let's do the first one. The first is you know, this. By the way, it's a typo. It's not valid. It's not valid. Okay, I'm gonna give you. I mean, you gotta be. Okay, so I'm gonna give you 20 more seconds. 10, 9, 8, 7, 6. Well, I'll just give you a minute for this. 5, 4, 3.
Was he counting to go away? Oh my goodness. Stop.
funny thing is that he was counting down before he got disconnected.
Have you seen a grown man cry?
Yeah.
Now you're seeing one. Ah, what a nightmare. But I'm still enjoying this lecture for some reason. I don't know why. I'm going to stop and pull. And I'm going to share the result. And most of you think it's not valid.
There's
Remember,
no
like this. Can you see? Can you see what I'm showing?
Yeah, we can see, but the answer is not on there. Like the answer should be n by n, right? But it's not on the full response.
We see your slides.
Oh, you see that? Can you see? I don't know. What's going on. Can you give me
Yeah,
feedback?
I think he was saying that it's not one of the options on the poll. Yeah.
the poll
That's
didn't
why I
have
must be
nx n times n, so
Oh, it didn't.
That's why most people
Oh,
put not valid.
oh, okay. Okay, sorry. All right. I'm stupid. All right, I'm gonna stop sharing here. All right, we'll just do it. Okay. I'm less excited, but let's do the second one. The second one, n by n times n by m. What about this one? Just write in the chat if you think you know. There you go. Wow, the chat is really running there.
Lots of m by m.
Yeah, m by m, right? Because first of all, does it work like this, like that? Yeah, it works. So the first and the second, so an m by m. And what about this one? Does this work? Well, one, but like this, like that, one by one. Yep. So the result should be m by n, right? A matrix. M by n, m by n. And then the last one, I have a 1 by n times an n by m. And second, this works. Okay, valid. So the result is going to be a 1 by m. Okay. All right. Now, in the first case, somebody asked, well, is an n by m times n by n gives me this, but if I commute them and I'm going to take an b times a, is it the same? Well, you can't.
The worst thing is, I don't know if he's doing this on purpose or not. I think so. It always
Just gonna cry.
he's suspiciously go out when he's saying something. So Mickey, are you back?
Yeah, but I don't think it's gonna be a fun experience, but let's see what happens. Wow, what a nightmare. Folks, please, I truly apologize.
So it's not a practical joke.
Not anymore. No, it's not funny anymore. Okay. Let's think now on things in a different way. Well, I'm just giving you breaks. I'm just giving you, toilet breaks. Consider this case. Consider a matrix equation, AX equals B. Okay. Well, A is a matrix, X is a vector, B is a vector. Okay. Well, there needs to be certain sizes that this should work, right? But let's just look at a times x. Okay, what is a times x? Am I heard okay? Yeah, okay. A times x, well, I can write a out, and I can say, you know what, a is an m by n matrix, and x, I can say, well, it's an n by 1 vector. Okay, that's a valid operation, right? We did this before, right? Okay, we did this before. So we can write it down. That'll give me an n by 1 vector, right? So this would be the result of multiplying these two. So what does it mean by equal b? Well, I'm just going to write it equal b, right? So basically, that means that I have this element needs to be equal to this element. I mean, this is the one single element right here. This is a scalar up here. And then the second element, that's another scalar, should equal to b2, and so on and so forth. Okay. Oh, wait, that looks familiar. That is a set of linear equations. This is a linear equation, right? A11 x1, A12 x2, all the way to A1n xn equals b1. I mean, we've seen this. We've seen this when we did tomography, for example. I mean, that's a linear set of equations. And here's another one. And here's another one. And you know what? I'm just going to write it in a different way. I'm just going to write it a different way. Ready? Oh, look at that. I just wrote it as an augmented matrix. Woohoo! You see? Nah, just kidding. I didn't disappear. I'm here. I just pretended to disappear. It's like peekaboo. You know, we have a saying in Hebrew. Basa, it's an Arabic word. It means like, you know, like a terrible thing. Sababa means like a great thing. So take the basa with sababa. Yeah, take the bad things with a good thing. Anyway, yeah, so I can just write it as augmented matrix. So okay, so these are just basically the same thing. This is just another way. AX equals B is just another way of, you know, writing the whole thing that we used to write before, either the augmented matrix or, you know, the you know, all these x's. It's just another way. AX equals B is another way of looking at exactly the same thing. So it's pretty exciting because this is actually how I think, or like, you know, in my research, or like this is like the first thing that we put on the board will be AX equals B. You know why? Because MRI is also can be represented by a linear set of equations. So I'll just put like the first thing we'll do AX1 is B, and then we have to put something nonlinear there just to, you know, spice it up, you know, but I'll mention that later. Okay. So, you know, when you look at matrices, I mean, it's just a set of numbers, right? But we can color them and put them in all sorts of very interesting way that will give us different interpretations of the same thing. But it's a really nice way of looking at this. So let's look at a row perspective of the matrix. What is a row perspective? Well, I'm just going to color the rows. And I have x's, which are the unknowns, and the b's, which are the results, right? Which are also a measurement. For example, you know, in the tomography case, you know, the b's were measurements. A were the coefficients of the system that we know what it is, okay? And then x's would be the unknown, right? So the row or the measurement perspective is what you've seen before. You get all of these and multiply by that, and then you get B1. And then all of these and you multiply by that and you get B2. So that is the row perspective, okay? So when I take this and I multiply like this, I will get A11 times X1. Okay, I'm gonna write it A12 times X2, A13 times X3, and that's what I get. Okay, so linear set of equation, the sum of these will equal that. So what does a row mean? A row in a matrix, okay, a row, if I look at the elements in a row, they mean how much the variables each variable affects a single measurement. Okay. So for example, let's say A11 equals 1,000, A12 equals 0.000001, A13 equals 0.000002. That equals B1. What does it tell me about B1? Well, it tells me that X1 is the most dominant contributor to the result. And I would have nicely wrote here, but A11, if it's bigger than the rest, that means that X1 really contributes more than the rest to the result that I just measured. Okay, very interesting way of interpreting things. All right, what about B2? Well, let's say A21 was equal 0, A22 was equal 0, and A23 was equal minus a billion. Well, obviously, X3 will then contribute in a very negative way to the measurement. Does that make sense? All right. Well, that's a really nice interpretation. So effectively now I know these coefficient A11, A12, they are kind of the weights that combine all those values into the measurement in this weighted sum. Now let's look at a column perspective. You know what I did here? I just colored everything differently. I mean, it's the same thing. I haven't changed anything. I just colored it now in the columns. This is a column perspective. And instead of coloring B1 and B2, I call it X1 and X2 and X3.
There's worse ways of punishing people.
Now take a look at this. A11 and A2, it's a column in a matrix.
Isn't she so
What's a column in a matrix also?
I can see why you picked her. Well,
Starts with a V. Yeah, it's a vector. This is a vector. And what about this guy?
Let me make her prettier for you, Louis.
What about this guy?
She'll be asleep.
That's a vector. And what about her? What about her? That's a vector too. That's right. All right. Well, I can just write it that way. Is that okay? Can I write it that way? I haven't done anything. This is like syntax sugar.
That guy don't die in this
I'm gonna mute all, if you don't mind.
Hey, so guys, I hope you enjoyed this series that we created. If you haven't done so already,
Mute all. There you go. I know you can unmute yourself if you want. Okay. So I got this. Isn't that? I kind of like the background sound though. Somebody talking. It felt like a classroom,
That's true.
right? Yeah. I kind of enjoyed it. I wish I didn't mute. Now it's kind of like, yeah, I'm like back in my like chamber. Well, at least I'm not like disappearing yet. All right. Okay, well, here's an interesting thing that happened here. Well, remember the like this and like that? Remember? Let's do it. This and like that. Well, look at the thumb. The thumb is pretty much pointing at the entire column, right? Like it's, it's going to sweep the entire column. So the thumb points to A1. And the thumb is always going to be multiplied here. The thumb always is on X1. So effectively, X1 is just going to be weighting the entire column of the matrix. So it's just going to be weighting A1. And what about my tiny finger? Well, my tiny finger is always going to be here, and it's going to multiply by X3. So the colors match. And so I can also write this in a different way, where X1 multiplies by A1 plus x2 multiplies by a2, and x3 multiplies by a3. The result of this, what is this? What is the size? What is this entity? It's a, starts with a V. It's a vector because A1 is a vector, A2 is a vector, A3 is a vector. They have to have the same size in order to be added together. They're vectors. Not a volcano. And so x1 times a1 is really a11 x1, a21 x1. And what is x2? Well, it's a12 a22 x2 x2. And what is x3 a3? By induction, she's a13 x3 a23 x3. So now you can see that these are just vectors added together. And then when I add them all, I mean, it looks exactly like the column, the row perspective, right? It looks exactly the same, except something here was a little bit different in the interpretation, because what we see here, that x1 multiplies, all the first coefficients, and x2 multiply all the second coefficient, right? And so on and so forth. Okay. So what does a column in the matrix mean? Well, a column in before in the row perspective, each element in the row was weighting the variables. Now a column says how a particular variable affects all the measurements. Okay, the column view interpretation is how a particular variable affects all the measurement. So if I look at, let's say now, x1, and I want to know, that variable, like, is it important or not? Is it, well, it's multiplied by a1. So I know how it affects all the measurements, right? Like if, for example, the values of a1 were large, that means that the variable now is going to have a significant effect. What if a2 was 0? What does it mean about x2, the variable x2? It's not important. It doesn't participate in the measurement. Like, it doesn't do anything. I could have basically got rid of it in my model. The model that I put x2 in because I wanted to solve for, not important. Not important. Okay, that's what it means. Okay, so it's a really interesting way of looking at things. One from this side and one from this side. Okay. Questions? Straight, if you want to ask, how about ask? Any questions? Somebody says, can we always think in one perspective? Yeah, you can, but you know what? When people think in one perspective, they don't see the whole picture. They only see their view. And that is valid not just for mathematics and algebra, and it's just valid for life. It's always good to look at a different perspective and interpret. It will give you a lot more intuition of what the situation is and what you're actually facing when you want to act or do things. Yes, Ria, speak up.
Yeah, I just had a quick question. So for the first perspective, for the row versus column, like row perspective, where you asked what each row means, and it was how each variable affects a particular measurement. So in this, each variable by that is like the A11, A12, A13, and each measurement is x1, x2, and x3, or is it the other way around?
So you're a little bit, let me explain again. Oh, great. Can you hear me now?
I think you froze for a second, but you're back.
Of course, first, because I wanted to speak. So the first situation, in the first situation, basically here we see the effect on one variable, right? So we see how the weighting of each of those variables, are affecting one measurement. In the second case, we see the effect of a single variable on all the measurements together. Okay, so it's slightly different, right? In one case, x1, we saw how much x1 affects, b1. Here we see a bigger view of how they affect the entire thing. Okay, it's just that it's not a different thing. It's just a different way of looking at it, which we're going to actually look right now. So let's look at a set of vectors, A1, A2. So I'm going to start using some mathematical jargon here. So jargon alert. But just bear with me. I'm looking at a set of vector. Well, how do I write a set? Well, I'm just going to put them in a wiggly, squiggly brackets, and I'm going to put vector A1 and A2 all the way to AM, and those are in. That's a symbol for in Rn. Okay, so this n length vectors, and how many do I have? I have m of them. And I also am given coefficients alpha 1, alpha 2, all the way to alpha m, and those belong to R1, right? They're just scalars. And I would say that the definition is the following: a linear combination of vectors the other way. B is a result of this linear combination, and that's the definition equal, and this is a symbol for definition, that B is equal to A alpha 1 times A1 plus alpha 2 times A2 plus all of these weighted linear combination of these set of vectors would result in B. Then that means that this is a linear combination, okay, just by definition. Okay, Mickey, why are you defining this? Well, Mickey, because I just want to remember, you remember what A times X is? Well, A times X is, this stuff. A times X was equal to, that matrix times that. And I was able to write it as A1, A2, A3 times that. And that turns out, a linear combination of vectors. So a matrix multiplication is by definition a linear combination of its columns. Right? That's what a matrix vector multiplication is, a linear combination of its columns. So let's say somebody in the late, I don't know, whatever hundreds, before matrices were invented, but vector, let's say, were invented, would ask somebody, it's like, oh, I want to compute a linear combination of vectors. And they're like, well, you have to write this particular way. And you know what? And then the inventor of the matrix would go like, oh, I got a better idea of how to write the same thing. I'm going to put it in this set of numbers, and that's going to be exactly the same. But you will be able then to look at it in different ways. And that other person says, oh my God, you must be a genius, because this is extremely useful. Okay? So linear combination of vectors. Now, why is that helpful? Yes, Aman.
Sorry, I don't know if you already said this, but in the previous slide, what did that like triangle above the equal sign mean?
Oh yeah, I said it's definition.
Okay.
Let's define this as definition. This is defined. This is just like, it's kind of like a, you know what GNU is? GNU, GNU. GNU, Unix,
Yeah.
GNU? With that. So GNU stands for GNU is not Unix.
Okay.
So it's a recursive thing. So here, definition. This is definition of definition. Okay, it's a recursive thing. I'm just gonna define the definition. Okay. Anyway, move on. All right, considering the problem AX, oh yes, Nithoran?
Yeah, I had a question. So r to the power of n, that's just real space with n inputs, but
I'm just gonna don't say R to the power of n, it's Rn. Okay, the R is space of the real numbers and its dimension is n. It is written as a superscript, but it doesn't mean power. It's just a set of vectors that have n numbers, n real numbers, okay?
so why in some slides the r is hollowed out and in some other slides it's not?
I couldn't hear that. Why in some?
Some slides the r is hollowed out.
Sometimes it's cross something, and that's when it's in the matrix form, we'll write M cross L, okay? So M times L. So the dimension of the matrix will be the reals R is the reals, and what is the dimension of the matrix? M times L. Does that make sense?
Okay, thanks.
Okay, so now consider this problem. AX equals B. And we're gonna, I mean, you've seen this, right? This is a linear set of equation. We can find a solution. How do we find a solution for this? Start with a G. Well, Gaussian elimination. Yeah, you could solve it by Gaussian elimination, right? Okay, to find out what is x1 and x2. Pretty easy. But we're gonna look at a different interpretation of things, okay? So here's a different interpretation. What is y1? 1. I can call it a1. What is 1 minus 1? Well, actually, before this, let's draw it, okay? Let's draw it on the graph. A1. There you go. Okay, this is A1. Have you ever seen a matrix being drawn like that way? Like now we drew a column of a matrix. Okay, all right. Well, what about the second column? Well, I'm gonna call it A2. And I'm gonna I drew it that way. So this is a drawing of the matrix. And what is A times X? Well, the result is B. What is B? Well, I'm just gonna call this B, right? This is B. Well, I'm just gonna write B. There you go. It's B. Huh. Let's look graphically what's going on. What is A times X? Well, A times X is really how much of vector A1 I need to add, I need to multiply. Yeah, exactly. And then add, that's right. Yeah, I feel like in a classroom, it's good. And then 2A2. A2. So how much I need to multiply A1 by something and then add it to A2 such that I will get the vector B. Do you see this? This is a different interpretation of the same thing. So how much? Well, it's kind of like, I need to kind of enhance this by, I don't know, like a factor of, kind of 2 maybe, and then add A2. Okay, so what linear combination of A1 and A2 will give me B? Well, I'm just going to add another one here. So it's 2 times A1. And I'm going to add it. I'm going to add A2. And ooh, I got B. Now, that wasn't easy because I have to kind of look and kind of eyeball it, right? To know what the value is. It's not a great way of finding a solution, but it's a really great way of interpreting the solution. Okay. So that is basically what it means. A times X is like how much A1 And how much from A2, add them together to get whatever the result is, whatever the vector of measurements is. You can also think of measurements as vectors. Okay? Very interesting interpretation. In this case, 2A1 plus 1 times A2. But I could also solve it using Gaussian elimination. So I'm just going to write the Gaussian elimination pretty quickly. Here in this first step, I subtracted this one from this one, and I got this. And then I normalized the second row, so I got this. And then I subtracted this from that, and I got this. So x1 equal 2, x2 equals 1. And that's exactly the same. No difference. No different whatsoever. Except that I have a different interpretation. And that is interpretation is important. You know why? Because remember when we did Gaussian elimination, and there was some cases where we had a solution, there was some cases where there was no solution, and there was cases where there was infinite number of solutions. Okay. The Gaussian elimination, all the steps really don't care what the B is, the measurement B is, right? Only at the end it matters if there's a solution or it's not, you know. Only at the end it matters. Like all the steps are done on on this matrix A. The vector B, you know, all these, you know, all these parts, you know, they just move around and change, and at the end will get, you know, will give us some interpretation. But all the operations are done on this part. And the thing is, you could stare at this and ask, you know what? Is there a solution or there isn't? Just by staring at this, is there a solution or there isn't? Or is it infinite? Or is it, you know, I mean, can I tell that from just looking at A? Is it a good A? Is it a good measurement? Or these are bad measurements? How do I know? Well, this type of interpretation is actually very important because it allows you to see if they're, you know, to analyze all of that. And let's just do that. Let's just try to analyze and see if, you know, what we can learn from this. What about this case? Same matrix, but now I'm going to give you an arbitrary B. Not a specific B. I'm going to give you an arbitrary B. And the question is, can a linear combination of A1 and A2, like, does this have a solution for an arbitrary B? Now, if you went through Gaussian elimination, you would get to some result, yes. But just by staring at this without Gaussian elimination, because, you know, if I gave you like a huge matrix, right, would you be able to say that? Well, let's see. If I have A1, I can move anywhere on this line by just scaling it, right? So let's say my B is, I don't know, the corner. I wish I could draw. Okay. My B is the corner over here. Okay. Well, A can take me along the line, right? Anywhere along the line, A can take me. So A is not enough. But then what A2 does, it allows me to take that line and kind of smear it in the diagonal and smear it the other way. And basically I can cover the entire space by some linear combination. So think about A1 being kind of like long because I can scale with arbitrary values, and then I can smear it different ways, and then I can cover any point. So I think I can definitely do that. We're going to discipline in a disciplined way, show you how to do it. But yeah, I think so. What about this? 1, 1, minus 1, minus 1. Well, what is A2? A2 is this. And the question is, can I, by performing this A times X, reach any point on the space, on B? Can I? No, because there's something iffy with this matrix, because A2 is actually A1 flipped. It's just negative A1. Well, then I can move along this line, but that's it. So there are some B's that will be able to find a solution if they lie on that line. But if my B is not there, then there's no solution. So you can see just by looking at the columns of A, I can tell you if there's a single solution and maybe an infinite solution if I know what B is, or no no solution if I know what B is. Okay, extremely useful. So I don't think so unless B is along A1. Okay, so that would be the answer. What about this? Instead of A2 being 1, 0. So now they're not kind of like orthogonal to each other, right? Well, now A2 is here. What do you think? Yeah, smear is kind of like schmear. You know, schmear is a Yiddish word for like, just spreading it and taking its little piece and kind of smearing it. You know, it's not really, I mean, it's not mathematical. It's like really just, like take butter, and like put it along a line and then kind of like on the bread and then like, you know what? But you don't see very well. So how about take like a chocolate spread, on a knife, put it on a bread and then, that's what we're gonna do with vectors. So you know what? I'm gonna do it again. So let's take A1 and it's aligned. That's my knife full of chocolate. And what does adding a combination of A2 does to that line? Well, it kind of moves it that way, but also the other way, but it doesn't really matter. I'm still gonna be able to cover my entire slice with this sweet, sweet spread of chocolate. Or if you're into it, Marmite or Vegemite. That's I love it. I love it. Marmite and Vegemite. Oh, yeast extract. Fantastic. If you're a Kiwi or marmalade, that's good. Yeah. If you're from Britain or you're a Kiwi, you'd dig on this Marmite. It's like this nasty thing. Anyway. So yeah, so in this case, I'll read yes. Yeah, you can still do it. You can still do it. Okay. That gives us to this definition, which I'm going to call a span. It's also called a column space or a range of a matrix. And definition. Span of the columns of A is the set of all the vectors B such that A equals B has a solution. Okay. The span of the columns of A is the set of all vectors B that has a solution. What does that mean? Well, it means that it's all the set of vectors that can be reached by all possible linear combinations of the columns of A. So I pick a B, give me a B. Oh no, give me a B. Oh, thanks. Oh, I got it. I got the B. Now I have a B. Now I'm going to take A and I'm going to try, linear combination. Didn't hit it. So it's not within the span. Okay. Now a different A. Oh, hit it. It's within the span. Okay, that's the definition. So here's an example. What is the span of the columns of A of this particular matrix? Well, let's look. This is A1, this is A2. What is, give me vector B, right? Any vector B in this case I could represent, right? Using a linear combination. So it's the entire R2, that's right, entire space. And now, oh folks, I'm gonna write something, you're gonna blow your mind. The span of A equals squiggly, squiggly brackets. That's mathematicians like to write squiggly brackets. Is the set of all vectors V. That's vectors V that, or such that V is a linear combination of some alpha times this vector plus beta times this vector, and alpha and beta could be any real number. Okay, this is exactly saying R2. That's the fancy way of saying R2 in this particular way. All right, what about this one? 1, 1, -1, -1. Well, in this case, this is A1 and A2. Well, can I reach all the points? No. So what is the span? Oh, what is a span? Well, the span is this line where x1 equals x2, you know, just along this line. That is the span. That's the solution. Okay. How do I write this? Well, I'm going to write it. The span of A is the set of vectors such that V equal to some scalar of 1, 1. Somebody can ask, hey, Mickey, what about beta -1, -1, -1? Where did you put that one? And I would then argue saying that, oh, you know what? -1, -1 is just the scalar of 1, 1, so I don't need it. Okay, it doesn't add. Yeah, it's Kermit. That's right. I'll do Rick and Morty some next time. All right, last thing. And we're going to finish it. Okay, ready? I'm going to define. Ooh, what is this? E. It's like a mirrored E. Well, a mirrored E means there exists. So here's in mathematics, okay? If there exists, that's E, that reverted E means there exists, just like substitute. You know, you computer scientists, you know, just equals that. If there exists a vector X such that X equals B, then B is in the span of A. Okay, that's by definition. The consequence for this is there's actually a solution. If B is within the span of A, there is a solution, right? That's the consequence. What if B is not within the span of A? Actually, let me ask you this. There is a solution. Is the solution unique? That depends. We don't know yet. You know, the solution doesn't have to be unique. Okay, but there is a solution. But what if B is not within the span of A? Then there's no solution. Let me just throw out there a hypothetical situation. Let's say you have a rocket, SpaceX, wants to get into orbit. Okay, and let's assume this is all linear equations. And I want to put it into the orbit. Okay, and I have these thrusts that I'm going to apply. And those thrusts are elements in this matrix. I'm going to apply a thrust in, you know, step 1 and another thrust in step 2. These are elements in the matrix. If the orbit is within the span of A, well, then my thrust, the thrust that I choose, based on, you know, what is their effect, the matrix is what their effect is, are going to bring me to orbit. So I just need to find what those X's are. But lo and behold, if that particular orbit is not within the span of that matrix, no matter what the steps I'm going to choose in order to apply the thrust and navigation, I would not be able to reach that. You know, you can think of it as a car model where now you're in a car and you want to brake, you know, or be able to turn and avoid, you know, some collision. What are the steps that you need to apply? If it's within the span, then you will be able to avoid. If it's not, all right. So there's implications about span. All right. So again, apologies for all the mess that happened. No, the slides are not frozen. It's me. I just kind of pretend to be frozen. Anyway, we'll see you on Thursday, and then we're going to talk about proofs of a few things that we're going to cover, and we're going to discipline go that. again, I apologize for all the glitches. I'll hope that glitches don't happen. I'm going to try to practice this. And we have office hours right now, so just move to the office hours, okay?
Mhm.
Sorry,
Great.
everyone.
Come and ask your questions in office hours.
Okay, thank you, bye.
You have a wonderful
you.
day.
Thank you.
Bye.
All right, thank you.
Thank you.
Thank you.